First, the component class. It's the abstract base for everything. It uses virtual functions so I can use polymorphism. This lets the engine treat a sprite and a transform exactly the same way. Next is the entity class. It does not hold data directly, it's just a container ID. It owns a vector of components and uses the template function getComponent. This follows composition over inheritance, so I can plug any feature into any object dynamically. Finally, the manager. This is where I improved on the tutorial. I changed the vector to use standard unique pointers instead of raw pointers. This handles memory automatically. I also added this refresh function. It physically removes dead entities from the memory every frame, acting as my garbage collector. For levels, I met the external file requirement by creating a map loader. This text file is just a grid of IDs, 0 for ground, 1 for walls. In load map, I use standard fstream to parse the grid. It iterates through the file and spawns the correct tile entities at the right coordinates. This let me edit levels without recompiling the code. For physics, I implemented the math in collision.cpp. This uses ABB logic. It checks if the rectangles of two entities overlap by comparing their x and y coordinates. I had a bug where enemies were getting stuck on items meant for the player. To fix this, I implemented collision layers. I separated entities into groups like group colliders and group map. You can see in this loop, the enemies are programmed to strictly ignore the group map layer. This filters the physics interaction, allowing enemies to walk right over the potions while still hitting the walls. For high score system, I implemented binary serialization. If you look at line 159, I'm using the standard iOS binary flag. This writes the raw memory bytes to the disk instead of plain text. To secure it, I added XOR encryption. On line 170, you can see the bitwise XOR operator being used with a private key. Because XOR is symmetric, this same line decrypts the score when the game loads. This prevents users from simply opening the save file in Notepad to cheat. Moving on to the gameplay logic, the physics engine is handled here in transform component. It holds the position and velocity vectors. In the update loop, I simply add velocity to the position. This drives the movement for every object in the game, whether it's the player, an enemy, or a bullet. For the visuals, I use the sprite component. It handles the texture rendering. To animate the characters, like the player running, I manipulate the source rectangle by shifting the X position based on the game timer. I can cycle through the sprite sheet frames to create smooth animations. To control the player, I use this keyboard event component. It listens for STL key events like WASD Crucially, this script doesn't move the player directly, it only modifies the velocity inside the transform component. This keeps my input logic completely separate from the physics logic. Now let's look at how I build the player. In the init function, I construct the player entity by composing those components together. Transform for the position, sprite for the player texture, collider so I can detect hits, and keyboard events to enable movement. For the enemies, I use a factory function. The core logic here is the AI tracking. I calculate a vector difference between the enemy and the player, normalize it, and apply that as a velocity. This creates a simple but effective behavior where enemies constantly hunt the player, forcing you to keep moving. When the player shoots, I spawn a bullet using the projectile component. It accepts a range, speed, and velocity. I implemented an important optimization here. If the bullet travels beyond its range or goes off screen, it automatically destroys itself. This prevents thousands of bullets from staying in memory and slowing down the game. When a bullet hits an enemy, I wanted a visual feedback, so I spawned blood particles. These are just small entities with random velocities and a very short lifespan. Once the timer runs out, they are automatically cleaned up. This makes the combat feel satisfying without causing memory leaks. For the interface, I created a UI label class using SDLTTF. This allows me to render dynamic text strings. I use this for the score counter and the health display, updating the texture whenever the value changes. To handle the game loop, I wrote this reset function. When the player dies or restarts, this triggers. It clears all active enemies and bullets from the manager and resets the player's stats to the defaults. This allows the game to restart instantly without reloading the whole application. I manage the flow using game states. I use a flag to switch between menu, playing, and game over. Inside the event handler, I check the state so pressing enter starts the game only if we are in the menu, or restarts it if we are on the game over screen. Finally, for optimization, I implemented delta time by multiplying velocity by dt, ensuring the game runs at the same speed on any hardware. I also profiled the memory. This flat graph proves my manager class is correctly cleaning up projectiles and particles with zero memory leaks.